Hello, everyone. Welcome to our 8th International Conference on Natural Resources and Sustainable Environmental Management and 5th International Conference on Water Problems in Mediterranean countries. Today, we will be hosting two international conferences. We will be welcoming various researchers from around the world, and we have some exciting topics. Today, we will be hosting 5 different sessions until 6 o'clock with local time. Today, now, Professor Dr. Muhammed Ercan will present you infrastructure master plan studies and reuse of urban wastewater.
Thank you so much. Good morning. Hello to everyone. First of all, I would like to thank you for the invitation for this conference. My name is Muhammed Ercan. I am the Deputy General Manager of Ankara Water Utility. Now I'm going to make a presentation about the master plan studies for the infrastructure services and the reuse of wastewater for the irrigational or the industrial purposes. Now, first of all, I would like to mention about the organizational structure of the infrastructure services in Turkey. Actually, there are mainly two bodies in the water services. The one side is related with the regulations, and the ministries of environment and urbanization and the climate change mainly prepare the regulations and publish the regulations that the water utility has to obey these regulations. On the other side, the local...
Muhammed Hocam, sorry for interrupting, but we lost connection with your presentation. Can you try to present again?
Now, sorry.
No worries, Hocam.
Okay. Tamam mı? Okay.
Yes, Hocam. Now it's okay.
Okay. Actually, there are mainly two bodies in the organizational structures of the water services in Turkey. One side is the regulation side. The ministries prepare the regulations and publish, and the water utilities has to obey these regulations. And the other side, the water utility, actually, basically in Turkey, the water utility is not only responsible for the investment, but also for the operations of these all infrastructure services. So the ASKI, Ankara Water Utility, actually mainly is responsible not only providing the drinking water services, but also responsible for sanitations and the stormwater services for the whole city. And these are some key indicators, the assess that the ASKI has. Mainly, we have the water resources. We have the surface water resources. So we provide the water from dams to the city center. In potable water system, actually, we have 21,000 kilometer water networks that operates by the Ankara Water Utility. In the sewerage sites, we have about 10,000 kilometers sewer networks and 5,000 kilometers stormwater networks. In a total, 45,000 kilometers water and the sewerage network is operated by ASKI in Ankara. When we look at the estimated urban water use in next 30 years, actually currently the agricultural use is more than the urban use. But in the next features, actually the urban use of the water is going to increase due to the increase in the populations and also due to the increase in the industrial water demand. So we have to focus on the urban use in the next years. And when we look at the water stress, as it is seen from the graph and the map, most of the countries is going to face a water stress in next years. Actually, these figures is more aggressive for the Turkeys than the most of the countries because the usable water per person in Turkey has been decreased rapidly over the years. So we have to focus on the efficient use of these water for the next years. And Ankara actually is one of the provinces in Turkey that water stress is most pronounced. Actually, when we consider the potable water use per person, the amount of the water is constant. On the other hand, the population and the water demand is increased, so the water per person has been decreased. And so when we consider the increase in the mean temperature, actually this graph is a World Bank's platform based on different models. The mean temperature increase for the Ankara actually when we look at the graph, the mean temperature is going to increase for the next years. And the other side, when we consider the precipitation, actually the precipitation is gonna decrease a little bit for the next years based on different water, different projection models. So we need to consider in the one side that the population is gonna increase, the water demand is gonna increase. In the other side, the effects of the climate change on the water resources has increased dramatically. So we need to consider these all effects and to prepare a roadmap from today to the futures. And also we need to consider the development of the new technologies, the need for the integrated planning, not for drinking water, because the ASCII is responsible for sanitations and the stormwater services. And so it is needed to plan, not to manage today. It's needed to plan to secure the tomorrow. So we launched a master plan studies in 2020, and we conclude all the studies and the planning in the last year to a kind of a roadmap for ASCII. Actually, the master plan studies was carried out under mainly 5 parts. The first part was related with the water supply and the water resource management. Second part was related with the distribution networks. And the third one was related with the water and the wastewater treatment plants. And the fourth one was related with the organizational structure. This is really important. And the fifth one was related with the financial analysis and the investment program. And these slides shows the detailed studies under each headings. Actually, I'm going to concentrate on the first one, the water supply and the water resource management. Under this part, the first important thing was the population projections and the projections for the water demand. The water demand and the water supply ratios, the climate change and its effects on the water resources, and also the potentials, how the climate change is going to affect our water potentials, and what's going to be the drought season in the next years, how we are going to project these drought seasons, and how we are going to manage these issues in the next years. And under the organizational structures, actually the operational cost of the water utilities has decreased. So we need to consider some new things to decrease the operational cost. So the asset management issues, the customer relations, the expectation of the customer, the expectation of the customers related with the service quality has increased. On the other side, the operational cost also increased. So when we consider the equation, ASCII has to consider in this one side to optimize the optimize the operational cost, and the other side ASCII has to consider to maximize the customer expectations. So all of these things are considered under the organizational structural part. So we are gonna we prepared many plans under these parts, and we have to consider how we are gonna implement these investment. We need to consider the tariff rates, the own resources, the loans. All of these things are carried out under the financial analysis and the investment programs. So for the water supply and water resource management, the climate change and its effects, water quality and the security, drought management, population and water demand projections, all of these studies were carried out under the water supply and water resource management. And in the water sewerage and the stormwater infrastructures, we concentrated on hydraulic model of the water, wastewater, and the stormwater networks, and the implementations of the investment in each 10 years, how we are going to implement these investment, what's going to be the capacity of the pumping station, what's going to be the capacity of the distribution networks and the collection networks. All of these things are managed under part 2. And in part 3, I mentioned that water and wastewater treatment plan are were analyzed under this part 3. And also the reuse of treated wastewater. At the end of my presentation, I'm going to mention about the details of these studies, the reuse of treated wastewater. And actually, in the master plan studies, we concentrated on to determine what's going to be the capacity of the water and the wastewater treatment plan, how we consider the discharge criteria in the wastewater treatment plan. In the next years, what's going to be the development in the discharge criteria in wastewater treatment plan? It is needed to increase. Is it needed to increase the upgrade the treatment process, and how we can use the reuse of treated wastewater? All of these things are carried on, out under part 3. Based on these studies, we decided that in the next 10 or the next 30 years, the capacity of the wastewater treatment plan, in each treatment plan, this capacity can be increased up to that level, or the capacity is going to be constant, or we are going to collect all the wastewater treatment plan and get rid of some small scale treatment plan. All of these things are carried out under part 3. Actually, as I mentioned, that the reuse alternatives for each wastewater treatment plan, the irrigation, recreational, or the industrial purpose, how we can prepare a plan for the wastewater treatment plan. And the organizational structure, as I mentioned at the beginning of the presentations, in water utilities, actually, the water, the infrastructure service quality in the customer side is increasing. And on the other side, the operational cost, the investment cost is also increasing. So we need to make a balance between the expectation, the water service quality, and the operation and investment cost. So we need to consider the assess management to decrease the operational cost, assess management in the maintenance, assess management in the operations of infrastructure services, the determination of the critical assets in the distribution network, transforming some operations in the digital platforms, the institutional capacity of ASCII, or the reorganizations of some departments, and the project cycle management, the educational policies, monitoring and the evaluation and the benchmarking system. Actually, we benchmark ASCII with the European Benchmarking Corporation in 2021 and 2022 to figure out the the strengths and the weakness of ASCII, and to figure out these, after figure outing these issues, we need to concentrate on that part. We need to concentrate it. We need to increase the capacity of ASCII in that part. All of these things are carried out under the organizational structures. And also we implement a pilot project for the assets management in one water treatment and one wastewater treatment plan in master plan studies. And the final part was related with the financial analysis. We planned many investment in drinking water, wastewater, and the stormwater side. So what's gonna be the strategy for the implementation, for the investment of these plans, the water and the wastewater tariffs, the financial model for the plans and the programs investment. I mean, how we are gonna implement these investment by using our own resources, by borrowing a loan from international institution, and what's gonna be the level of the water and wastewater tariffs. We need to concentrate it on the on the water and wastewater tariffs. All of these financial models for the plans and the programs was carried out under the financial analysis and investment programs. I'm going to mention about a summary on the population and the water demand projections. First, the population projections. We prepared this 3 scenario for the population projections: low scenario population growth, main scenario, and the high population growth. Based on these population projections, actually, we projected that in 2054, the metropolitan city center of the Ankara is gonna increase up to 8.4 million. For the whole city, we projected that the population reach 9.4 million. On the other side, we projected to the water supply and the water demand based on the current water resources, and based on the projection in the water supply and the water demand, we figure out the gap between the water supply and water demand. So when after the figure out in the water supply and water demand, we need to concentrate it on the water alternative water resources, how we are going to manage this gap, and how we are going to provide the needed water up to 2054 from which water resources. And also we need to concentrate it on the drug probability. In the next 30 years, what's going to be the drug probability for the Ankara city. So we created model to project the drug probability. We modeled the drug probability projection based on the observed precipitations. And this figure shows the drug season in the last periods in Ankara from 60s to 2019s. Based on this observation, we modeled the expected dry periods in Ankara in the next 30 years based on the SPI, different SPI index. So when we look at the graph in 2037, we are going to face a drought season based on these different projections. And this is the severity of the drought season in the next 30 years. In 2037, 2038, we are going to face a severe drought in Ankara. So we need to consider these periods for the water supply. And this is the severity. This graph shows the severity map in the 2037. Whole city, the whole city is going to face a severe map. And in 2048, the north part of the city is going to face a severe drought. And also we projected the temperature for all water basins, for whole dams that we provided the water. Based on different projection models, we projected the change in the temperature, the increase in the temperature for each dam basin. And also we projected the flow for the water basin. This is very important for the water supply because we need to take into account the effects of the climate change for the water bodies when we add all the water resources. I mean, what is the current capacity of the water resource capacity of that dam? So we need to consider the effects of the climate change, and we need to consider we need to take into account the effects of the climate change for these water resources. And the reuse of wastewater project, as I mentioned before, actually for each wastewater treatment plan, we prepared a conceptual design for the reuse of wastewater because the effects of the climate change on the water resources is increasing. So we need to use all water as much as possible for different purposes. So for each wastewater treatment plan, actually we prepared conceptual design for the wastewater treatment plan. Actually, for some wastewater treatment plan, it's going to be used for the irrigation. For some wastewater treatment plan, it's going to be used irrigation and the industry. In using the wastewater treatment plan in agricultural purposes, actually there are different institutions or the different organizations in Turkey. At the center, the water utility is going to provide the reuse of water, and the Minister of Agriculture and the Forest, the General Director of State Hydraulic Works, Minister of Environment, the irrigation unions, the provisional directors of the agriculture and the forest. All these different organizations has to collaborate for the use of the agricultural purposes in the use of wastewater. And the regulation, when we consider the regulations in the Turkey, actually there is a national target that up to 15% in 2030, the Turkey has target to use the reuse of wastewater. And also there are some regulations related with the quality the quality of the reuse of wastewater in the irrigational purposes. And this is the regulatory criteria in Turkey. Actually, this is important. When we consider the unit cost in the treatment plan, actually the operational cost of the reuse of wastewater plant is about just 20% of the operational cost of the wastewater treatment plant. I mean, actually, the water utilities has to consider the operational cost of the unit price of reuse of wastewater, because just 20% of the increase in the operational cost is going to create a huge amount of the water for using of irrigational purposes or industrial purposes. Actually, ASCII currently has in progress 4 main reuse project. Two of them are medium scales, and the central wastewater treatment plan reuse project is a really huge project, and currently we are preparing the detailed design of this project, and I'm going to mention it in the next slide. The first project is related with a small scale or the medium scale project in the Beypazarı region, and we are going to use these reuse water for the irrigational purposes, about 4.5 per day, and we are going to use this water for the irrigational purposes. And this is the units in the reuse side. Actually, this project was developed 4 months ago. We provided the raw water for the Kazan Soda company for the processed water, but due to the decrease in the water level in our dam, we restricted the providing the raw water from our dam, and we developed this project to use treated water for the processed water for Kazan Soda company. Actually, currently we signed a protocol with the company, and we are going to pump the treated water from our wastewater treatment plant to the factory site, and the company is gonna implement the reuse units, and about 9,000 meter cube per day treated water will be used as a processed water. And this is the last project that ASCII focused on for the implementation of reuse of water. Actually, this is a huge amount of the project, and with this project, we are going to implement a huge reuse units. The main units of this project are inlet structure, rapid mixer, slow mixers, clarifier, the sand filters, and the UV unit. With the implementation of this project, actually, we are aiming to use about 440,000 meter cube per day in the first phase, the reuse of wastewater for the irrigation and industrial purposes. In the slide, as it is seen, some of the irrigational area is gonna irrigate by the gravity flow, and some of them is gonna irrigate by the pumping. But this project is gonna be a good example, not only for the Turkey but also for the all over the world, based on the capacity. Actually, at the downstream of this treatment plant, this is the central treatment plant, we have huge amount of farming areas. So we are lucky that we have these amount of the farming areas that we can use wastewater for the irrigational purposes. By implementing actually mainly this project, this project will provide existing drinking water sources will be protected. The sustainable and uninterrupted agricultural irrigation will be carried out in the project area. The uninterrupted agricultural irrigation, actually, the reuse project, when we consider the water supply security, the reuse project will provide uninterrupted water supply. Similarly, the processed water will be supplied uninterruptedly for the industrial productions, and the water supply security will be ensured for both sectors in the projected area. This is the end of my presentation. Thank you for your attention.
Thank you very much, Muhammed Hocam. Thank you very much for your contribution to our conference. We would like to see you again in our next conference as well. Thank you very much.
Thank you. Thank you so much.
Thank you. Dear all, our next presenter will be Professor Dr. Necati Ağıralioğlu. Necati Hocam. Necati Hocam, can you turn on your camera and your microphone, please? Yes, Hocam, now we can see you.
I want to share my presentation.
Yes, Hocam, we can see your presentation as well.
Thank you very much. Okay. Good morning, dear Chairman, ladies and gentlemen. I am Necati Ağraloğlu. I prepare a study related to Cyprus Island. The title of my presentation is as Assessment of Water Resources Potential and Demand on the Island of the Cyprus. Now, maybe you can see the screen. Freshwater resources are the fundamentally dependent on precipitation. In the islands of the Cyprus has experienced water scarcity and throughout history. Several studies have been conducted to determine Cyprus' water potential, and some of them have been conducted on Cyprus water resources, and some of them related to climate change in Cyprus. Now, in this study, we are interested in the present and future water resources potential of the islands of Cyprus. And so we also determine the water demand of the both northern and southern Cyprus were examined. Furthermore, we want to estimate the current and future water deficit of the island. Now, maybe you can change this one, slide one, sorry. You can see the Cyprus map, and we divided the Cyprus mass into two parts as Northern Cyprus and Southern Cyprus. The title is, the first one is the Turkish Republic Northern Cyprus, and the other one is the Greek Cypriot Administration of Southern Cyprus. So, the water budget equation was used to determine the water resources potential in Cyprus. In order to estimate potential evaporation in Cyprus, we use some methods, and Blanet-Crittall and Hansen method and something like that. And also we use Kendall's and Shan's methods for future trends. In this study, many data are used, measured data for temperature, for precipitation, for evapotranspiration, and population were collected from literature. The future population estimation of Cyprus, the world average annual population growth rate are used for this project, for this study. So we are interested with climate characteristics. Cyprus climate is typical of the Mediterranean region, which can be described as semi-arid climate. Meteorological and climate data are measured at a total of 99 meteorological stations on the islands of Cyprus. 33 of them is northern part, and 66 part of them is on southern Cyprus. And in Nicosia, in Cyprus between 1991 to 2020 were used to represent the climate of Cyprus. Accordingly, the average annual rainfall is 332 millimeters, and the average annual temperature is 20.1 centigrade degree. And so this is the general information about this system, and maybe we will continue. You see the temperature of the northern Cyprus, the average temperature between 1975 to 2020 is approximately, as you see here, as 0.80 point centigrade. For each 10 years. And so you see the figures. This is the northern Cyprus. This is the average daily temperature. This is the minimum. This is the maximum values. And also, we are interested with northern Cyprus as a precipitation. You see the precipitation between 1991 to 2020, and you see there is a trend, positive trends like this one. So, and the average precipitation of northern Cyprus between 1991 and 2020 was 380.6 millimeters, and the value of the estimated to decrease by 36 millimeters between 2021 and 2050. And so there are some other explanation related to potential evaporation in Cyprus, northern Cyprus. You can see that we use some methods, Hammond methods, Tronholt, and Blaney-Crittell, some others. For each month, we plot the figure like this. And especially, you can see in the northern Cyprus part, potential evapotranspiration values calculated by between 1981 to 1998, and it was estimated in this figure you can see here. And pan coefficient for northern Cyprus is also measured. You can see here the pan coefficient is changed in this period between 0.52 and 0.67. You see this figure as this one. So in southern Cyprus, they also consider the temperature and precipitation. We obtain some values. You can see here, for instance, temperatures and precipitation change in the southern Cyprus were evaluated between 1981 and 2018, and we can see the average will be 18.3 centigrade degree. So, furthermore, we can also obtain the mean annual precipitation as 475 millimeters. And evaporation is also considered. And so here you can see pan coefficients in southern Cyprus. You can see the values per each month. You can see, as for instance, in January, 0.72 pan coefficient, and this is almost the critical point. But you can see also there is a trend in the pan coefficients in this figure. We use Shen scheme and we use also Kendall scheme method. And so you can see temperature and you can see precipitation also here. I can summarize this one according to study. We can see some values from this one. Cyprus will be affected by rainfall decrease, then it can be reached to 30 millimeters between 221 and 250. This is the critical point, and so. And so we are, maybe just a minute. They are interested with Cyprus population. Population in northern Cyprus, we assume some growth rate as corresponding to world growth rate. And so, for instance, you can see annual population growth of 0.8% for the first 10 years and 0.7% for the second 10 years and 0.6% for the third years. And you can see at the present population is this one, and the end of this period is, for instance, this one. Sorry, just a minute. Anyway, we can estimate the population in northern Cyprus, population of southern Cyprus, and then population of the total entire Cyprus island. There are some tables calculated and presented here. And so existing and future available water resources and water demand, we estimate precipitation values and temperature values. And you see here northern temperature in 1920 is this one, 18.7. In 1950, 19.7. The change is 1 centigrade. Southern Cyprus, similarly, you can see 18.3, 20.3. The change is a positive 2.4, and totally you can see the change is plus 1.5 for temperature, these values, annual temperature centigrade. Annual precipitation, you can see some values. For instance, this one in the northern Cyprus, the change is minus 36, southern Cyprus, minus 40, and total islands annual precipitation is minus 30. And depending on these values, we can estimate the Cyprus precipitation volume as million cubic meters. You see here some values. And sorry, this one for northern Cyprus, for southern Cyprus, for total Cyprus, and you can see the values of total precipitation volume, million cubic meters. And water balance, we use water balance in Cyprus. You can see in northern and southern Cyprus, water balance, as for instance, mean annual precipitation in million cubic meters, and groundwater recharge is this one, and runoff, actual evapotranspiration, and total water abstraction is for 2021 in northern, 2050 in these values, and for southern we can calculate these values. You can see, maybe you can, later on you can look at these tables. Water demand, there are many estimations for water demand in Cyprus, but in this study we assume that daily per capita consumption was taken as 150 liters per day. It was also assumed that the 15% of the value will be the household purposes. And some other, you see it for tourism, for industry, and for agriculture. Agriculture is the maximum value, is 68%. And so depending on these estimations, these assumptions, we obtain the water demand in the island of Cyprus. For instance, you see the water demand 220, water demand 250 for northern part, for southern part, for total part. You see the table here for tourism, industry, agriculture, and other water supply of all of them. Water deficit also estimated. You see here for water estimated for deficit, million cubic meters per second for islands, northern Cyprus, southern Cyprus, total Cyprus, also here. You see here years 2021 for northern Cyprus, and million cubic meters. Total water abstraction is 128 million cubic meters, and demand 140 million cubic meters, and deficit you see is this for this period. In 2050, our total water abstraction will be like this, and demand will be like this, and deficit will be 56 as a minus. Similarly, for southern Cyprus, we obtain some values, and total, especially you can see between this 2021 and 2050, there will be some deficit increases. At 2021, our deficit will be 62, and in 2050 will be 207 million cubic meters. And evaluated, there are some studies, there are some dam construction studies in both part, in southern part and northern part. And so you can see there are some values, sorry. For instance, between 1974 and 1984, there are some studies in northern Cyprus. The total capacity of the reservoirs is this value, as you see. Also in southern Cyprus, there are some construction dams, and you can see they totally increase this value. And some studies have been conducted in northern Cyprus, and so there is a study finished in 2015, and 75 million cubic meters of water was transferred to Cyprus from Turkey as a water supply project. And also in southern part, there is another big project conducted after 1974. And so this called as Cyprus Southern Conveyor Project. But all these values don't get enough water from both sides. There is some deficits in Cyprus, as you described previously. And so, as a conclusion, you can see here, especially the total water demand in northern Cyprus for 2021 is, you see, 140 million cubic meters. And in 2050 will be 1,072 million cubic meters. And similarly, there is some results for southern Cyprus, and so water demand in northern Cyprus will be 330 million cubic meters in 2021 and 4,007 million cubic meters for 2050. And so we estimate also the water resources potential and some other values between this period. And so we can get some results as you see in this part. This is the end of my presentation. Thank you very much for your listening to my presentation. Okay.
Thank you very much, Necati Hocam. Thank you very much for your valuable contribution to our conference. As always, we would like to see you again on our next conferences. Thank you very much. Any question will be directed to your email.
Thank you very much also from me. Okay, thank you.
Dear researchers, our next presenter will be from Japan, Sohei Kobayashi.
species living. Floods promote coexistence of species, improving the habitat quality, and also the main flow floodplain connect. Hello, my name is Sohei Kobayashi. I'm an associate professor in Kyoto University, Japan. My topic today is the role of floods in sustaining diversity of aquatic habitats and river floodplain connectivity. This photo shows the example of aquatic habitats in rivers. Outline, I first talk about the biological community in river ecosystem, followed by the role of floods, several roles of floods in the ecosystem, and finally the ecosystem response to climate change. This is a key question I want audience can answer at the end of my talk. How do floods enhance species diversity, both directly and indirectly, through their effects on the habitat characteristics? This is what you can see in river ecosystem. The biological community includes several groups like fish, birds and mammals, benthic invertebrates, including aquatic insects, and benthic algae. And each group have many species, like 100 of species included in each group. And they construct food web or ecological pyramid like this. This is how rich the invertebrate species in rivers. Each site have many species. Mayflies, stoneflies, caddisflies, they live in reef falls, fast flow habitats, from 40 to 60 species. Water penny, dragonflies, and non-insects live in pools, slow flow habitats. They also have 40 to 60 species. So usually more than 100 species co-occur at individual sites in Japanese rivers. Bed grain size very important. They live underneath the stones or the sand, and they prefer fine grain size or coarse grain size, depend on the species. As a total, invertebrates biomass and species richness is maximized at Kobo riverbed compared to other riverbed. So riverbed grain size determines benthic invertebrate abundance and species occurrence. Now I talk about the role of floods. This is an example hydrograph. There is normal flow period and also flood. Flood decrease the number of invertebrates according to the magnitude of flood. This shows the decrease of invertebrates depend on the magnitude of flood. Larger flood, more decrease of invertebrates. Flood always reduce benthic invertebrates, but in the short term. How about in the long term? Intermediate disturbance hypothesis by Connell explained that the local species diversity is maximized when ecological disturbance, like floods, is neither too rare nor too frequent. Too rare nor too frequent. It is maximized at the middle disturbance frequency. So floods can increase benthic species diversity in the long term. Why this occurs? This is one mechanism of the intermediate disturbance hypothesis. There are two types of species. One is a R-strategy species, which can quickly colonize, disperse, move, and rapidly increase, but weak competitively. K-strategy species, on the other hand, they cannot move quickly or increase quickly, but they are competitively strong. In the disturbance-rare environment, the stable environment, this K-strategy species win. When the disturbance frequency is high, R-strategy species win. Both two types can coexist under moderate disturbance, moderate frequency flood condition. So moderate disturbance enables the coexistence of different species. This is one of the important roles of floods, enable the coexistence of species, different species. Another role is the quality of habitats. They change. In the normal flow, during normal flow, the invertebrates can grow, but algal mats or organic material accumulate on the riverbed like this. And also the riverbed will be clogged by fine materials during the normal flow. Decrease the habitat quality during the normal flow. In small to medium floods, they occur several times a year. They wash, accumulate organic matter or fine materials, and they clean the riverbed, improving the habitat quality. So this is important. However, they can also partially erode the riverbed like this and remove the important habitat for invertebrates. This is a negative impact. This is an example that displays the riffle mound was removed by the small flood. Lot of large floods. Large floods occur once every 3 to 5 years or less. They flush the sediment, but they also deliver new sediment and create the habitat which was lost by the small flood. So improve the habitat quality again. However, the many invertebrates and fish are killed during large floods. This is how invertebrates increase or recover after the floods of different magnitude. For small floods, they recover within 1 month. But for the small to medium to large flood, it takes more time, like several months or several years for invertebrates to recover. So different flow states have different roles. Normal flow is important for the growth of for the biota, but they reduce the habitat quality by bed clogging. Small floods, they flush and clean the riverbed and increase the habitat quality, but also they cause bed erosion, which decreases the habitat quality. Large floods provide sediment again and create and increase the habitat quality, but they kill invertebrates. So ecosystem needs all flow state for the sustainability. This is another role of floods. They connect between main flow and floodplain. Most of the biota, fish and invertebrates live in this main flow, but they have to migrate to these floodplain ponds or tributaries for reproduction, for making eggs. And sometimes when the condition of rainfall is bad, for example, during the high turbidity or high temperature, they escape to the tributaries. So the rainfall and floodplains should be connected. But the connectivity depends on the location of the floodplain habitats. If the location of floodplain habitats like pond is close to river, the flood can connect rainfall and pond easily. But when the ponds located in a higher elevation, it needs larger floods to connect the rainfall and pond. So depend on the location of pond, also the channel shape. Insist river channel needs larger floods to connect between rainfall and flooding. This near the water level at the base flow is very important place, but they change according to the river shape. The riverbed has been insisting many rivers due to a lack of sediment caused by dams and sand mining. This is an example, one river in Japan, the riverbed cross-section. In 1960s, the riverbed is very flat and high, but due to the dam construction and sand mining, the river is insist and become deep. And accordingly, some habitat availability changed. The land close to water, like 0 to 0.7 meter above the water, shown by gray, decrease year by year. Also, the shallow underwater decrease, light blue line is decreased. This is called by the channel shape change, and which is caused by the sediment deficit. Aggradation and degradation is very important to understand the ecosystem status. Aggradation, we call, this is when the riverbed increase by sediment deposition, and degradation, when the riverbed is decreased by sediment erosion or incision. The ecosystem status change by this degradation or sediment availability level. This is a channel form, river shape form, and this is ecosystem function. Ecosystem function is always best at the middle state of this gradation or sediment availability. The response of habitat diversity and ecosystem functions can be predicted based on the present river status and riverbed gradation. The response to climate change and human impact. It is difficult to predict response to external factors, but the direction of change can be assessed in terms of degradation and aggradation. For example, climate change, if the extreme rainfall increase, then landslide and slope failure increase in the mountains, which cause aggradation. And we can predict how ecosystem function change by this aggradation. When the global warming exceed, then the forest, which promote the forest overgrowth, then the channel becomes degraded, and we can predict how the ecosystem change by this degradation. Okay, this is a summary of the role of floods in river ecosystem. talk about the many species living. Floods promote coexistence of species, improving the habitat quality, and also the main flow floodplain connectivity. Aggradation and degradation is important for predicting the ecosystem. This is the end of my slides. I hope you can now answer this question. Thank you very much for your listening.
Thank you very much, Professor Dr. Kobayashi, for your contribution to our conference. We would like to see you again in our next conferences. Now, our next presenter will be Professor Dr. Alper Baba.
Good morning, dear Chairman, ladies and gentlemen. First of all, I would like to thank you very much for inviting me to this important conference on water problems. Today, I'm going to focus a little bit about the effective use of the groundwater resource and importance of recharge for the development of these resources. As you see that the global water use has increased sixfold in the last 100 years. Most of them consist of the agricultures, after then industry, and then last one is the domestic. Agriculture still is increased in the world. The second important parameter is the population. The figures show that the population distribution of each continental, as you see that most of the population, almost 60% of the population of the world located in Asian countries. It is predict that 10 billion people will live in the world in 2050. And then when we compare the population with the water resources, this is the quite risk for some continental according to this data. And then if you look at the sectoral water use by continental, as you see that the first picture show that the world average and the world 69% of agriculture, just like a 19% industry, and then just 12% domestic. But if you look at the Asian countries, like about 80% is for the agriculture, 10% industry, and the other one is for the domestic. But when you look at the Europe is about 55% is the industry, just 25% is agriculture, the other one is the domestic use. But when we look at the water demand per sector, use a percent of the total water demand for each countries, it's quite different. For example, in here, as you look at the Croatia, for example, about more than 80% they use for the household. But when look at the Egypt is like about 80% just used for the agriculture. But when look at the French, you see that just most of the French people use for the for the industrial water resource and for cooling water system. When you look at the other countries, it's quite also different. Look at Morocco again, is like more than 80% they use for the agricultural system. And then if you look at the application water resource, how did the civilization improve? The way water resources have generally been utilized through the history. And then during the history, the people used to different, they collected water, they used different methods. For example, at the history, the individual domestic rainwater tanks, that the people collected rainwater, and then people located wetland area, and then also people collect and store water underground. We call that underground groundwater storage. Have been built, especially in the Istanbul region, in the Anatolia. And then also some people collected rainwater and treated wet water they use for the industry. In addition, most of the cities, most of the town, most of the village settled close to the the rivers. And then also from history to up to now, the people built the big dams for energy, for the agriculture, for industry. And then if you look at the irrigation, and then if you look at the irrigation land of the in the world through the history, because the people used in the history the land, agricultural land, but most of this land is directly related to water resource because all the land located near the stream at that time, located near the water resource. Then they used different technology in in the different part of the earth. The other important parameter that the water quality. Therefore, from history to up to now, the people use from the the desalination. That you can imagine from Mediterranean to the ocean, people use the ocean, that ship, but they need the water, but they treated this water for the system. In addition, some water very dirty. They use some clay material. They absorb some contamination in this area. The sanitation, that is very critical, and then sustainable water resource, they were hygienics, that they used the sanitation technology, they improved the sanitation system. But this from prehistoric to the present times and the futures, we have some papers about this one. This is a very good review about the problems. If you look at in here, the figures, you see that the first Mesopotamian peoples, they used, the good sanitation system. And then after that, Greece, the Greece people, they increased the system, organized the reuse, and, this kind of the problems. And then after then, you see that until the, last centuries, that especially in 1950s, we have now advance of the centralized wastewater treatment in the world. And then this has affected the rate of the earth, rate of the date. Look at in here in 1900 at the time, the many people was passed away because of some earth problems, but with contamination problem, water problems. But until if you look at the 1980s, after the 1980s, especially after the 1950s, you see that this rate is going to be decreased because we drink the good quality of the groundwater resources in the system. If you look at the, if you drink the hot, good quality water, this affects your life expectancy. These pictures show that how the life expectancy changed from the time. As you see, until 1950, people live about just about like 40, 50 years old. But now the life expectancy, that increase for ladies is to reach about 88 to 83. Men is to reach about 78%. But in addition, you see that until 1950, we have just 2 billion people in the world. After that, the population is going to be increased now. At that time, population more than 80 billion in the world. But this is directly related with the quality of the water resources. The other problems is that climate change. We know that the climate change affected the everything now. And then we are now living the coolest period of the Earth's crust in the 65 million years to now. And then you can imagine 60 million years ago, the Earth, the crust temperature is about 12 degrees, and then it's going to be degrees. And then in 30 million years ago, as you see that this is around 3 degrees, but you see that it's going to be degrees. But when you look at the 400,000 years data from up to now, as you see that this figure shows that the carbon dioxide concentration with time, as you see that in the 4,000 years ago, 200 the carbon dioxide concentration 280 ppm, but now it's going to increase. I will show you in the next slide. But you see that that the concentration, that the distribution of the concentration and distribution of temperature is proportional to each other. That it's very, that parallel to others. But it's interesting in here, that we can see that every 600 years, time shift about the climate change in the system. And then if you look at the 2000 data, we got very good data after the French Revolution data because we meteorological data. Now we are living the hottest period. That we are as you see that in here, the temperature is going to be increased, and then our centuries. And then before this one, you see that we little ice age in the world. And then all the projections show that that this climate change, this temperature increase, more evaporation, and this affected the water resources. They make a water stress. And then if you look at the Mediterranean part region, especially like also some Asian regions, especially the area is extremely high. That this is meaning that the water stress is very high in this region. And then this is show that this part of the site is the red one is really extremely the problems for the near futures. And then therefore, at the time, many people used the groundwater resources. Groundwater resources are very critical. They have many monitoring wells in this area. 21st century groundwater level trend globally distributed and monitoring in some regions. You see that this is some point. But when we look at the data, 21st century aquifer scale, you know that the depth of water is going to decrease, especially percent of the aquifer system in which groundwater level have deepened faster than 0.5 meter per year. For example, in arid region is like a 20, from 23 to 41% is going to decrease, and then in the hyper arid, you see that still is near the 20% is going to be decreased in the system. And then if you look at the recharge projection, you see that climate change affected really groundwater recharge rate, but you see that the red color is the minus, meaning that the low recharge. As you see that, especially the Mediterranean part and that some of the region, that's really very critical. That not enough, that feed the groundwater resources system. We did studying about the Turkey. We collected all the, collect data from the groundwater and the monitored groundwater level. As you see that this all data, that the maps, they have some red colors. This is the show that the groundwater level is going to be decreased. There has been a serious decrease in groundwater level in the basin in recent years. You see that especially in this part, we have a very big problems for the groundwater level because of this. In addition, you can see that in the some, the graphs, groundwater level with time, as you see that how groundwater level is going to increase. At the time, it's really it decrease more. You see that many years ago, just like this one is like you see that a minus 30, but now it's minus 60, minus 70. And then not just in the Turkey, you can also see that it's a problem in Morocco. You see that how the groundwater level is going to increase. Lebanon, again, you see that how the related with time and change. Spain, the groundwater level will be changed and then it's going to decrease. You can see Tunisia, groundwater level is related time is going to decrease at that time. You can see many systems. Okay, therefore, the recharge is very critical. Groundwater recharge is very critical. Groundwater recharge techniques used to enhance natural recharge of the aquifer by facilitating the infiltration, percolation of the water into the subsurface. These methods are commonly classified in natural and artificial recharge approach, depending on the level of human intervention involved. Natural groundwater recharge occurs through the precipitation, river, lakes, infiltration return, flow, where water slowly infiltrates through the soil and rock layer to reach the aquifers. Also, artificial and managed aquifer recharge methods are intentionally designed to increase groundwater storage by direct surface water, storm, or treated wastewater into the aquifers. At the time, we used well-based research methods involve the injection water direct into the aquifers, recharge wells, injection wells, recharge shafts. Also, rainwater harvesting-based recharge methods collect the roof of surface runoff and convert into the recharge pits, and then or recharge wells. In recent years, treated wastewater used for the recharge and gain attention as a sustainable approach about groundwater resources. This is some pictures, that about the karstic system. You can see that underground we have many pore system, maybe have many caves, and then we can recharge the system with the surface water system. Groundwater recharge cannot be measured directly to large scale, so it is typically estimated using field measurement, indirect indicators, and modeling approach. One of them is the water balance method. This is very, the common methods. We, check the, budget of the water system, and then according to this one, we calculated the, the recharge system. In addition, we can, that we can just use the soil moisture-based methods, and then also use the water table application method. This we can see how the rain, according to precipitation, the values will going to increase, and then we check this one. And then also we can use some trace-based method. It's very critical and very important to give about the hydro other parameters. As I mentioned, that water balance methods, which is estimated the residual of the hydraulic budget, soil moisture-based method, estimated recharge by monitoring changing soil content over the time using sensors. At the aquifer scale, water table fluctuation method is widely used. Recharge is calculated for observed rise groundwater level multiplied by the aquifer specified yield. And the trace-based method, we use two different, the tracer, like isotopes, chloride mass balance, and tritium are commonly applied. With stream flow-based method, estimated recharge. Yeah, this is the karstic system, that they recharge to the karstic area. This area, look at this one of the plane. This is, you can imagine this agriculture field. Sometimes, that we can see flooding in the region, but this system is the karstic. It's important to, there may be more water they recharge in the system in area. Let's just show that one of the movies about this one. As you see that this old agriculture field, after the flooding, locate, the water cover every part. And then it's important to, that some people drain this water, directly go to the sea, but we want to collect this water and reject it to underground system. But when underground system, sometimes we can use some valves. You see that some valves, and then recharge the karstic system. This is some cross-section about region, but it's important to, you have to filter this one. You can maybe use some valves, and then after that you inject the underground system. This is sample from this region. You see the karstic system, and you see that some, valve in the field, sample of the valves of the region. When recharge groundwater, pollutants must be minimized. Otherwise this can cause even bigger problems. In agriculture area where large amount of fertilizer and pesticides are used, the quality of the water must be monitored accurately and effectively before recharge of the groundwater in this area. And then the other one, it is possible you can recharge the groundwater in the waddle zone. For example, some stream. If you have a stream in especially the rainy season, you can change the direction and then put this water for the underground help them system. For this one, some study was done in the Western Anatolia. Again, we built some pond. Look at like this kind of pond, and then in the pond, it's important we have to measure how the groundwater level be changed later time, and then how this water affected other system. Therefore, there is many wells. This study was done by Turkish Water Institute. And then in this water, we can measure to all the, the parameters, how the groundwater level will be changed later time, and then how the velocity, hydroconductivity will be changed in the time. And then for this one, we used some tracer, look at this tracer instrument of this area. And then we use uranium and taurine, fluorescein. You see that this is our tracers. We just inject in here, fill with water, and then we just monitor the other place, how they behave. Look at this is some sample, that our field studies. In addition, it's the monitoring all these parameters. In addition, monitor all these parameters like electric conductivity, like the uranium values, like the other parameters. We have many values in here. And then other study was done in Alaşehir Basin. It is very important place also. In this kind of the study, that you have to install research well, you have to obtain hydrological parameters, you have to, the sample, groundwater and meteorology data. And then after that, you can use this chemical analysis for model. And then after that, you use some numerical model generated with the JS-based methods. For this model, it's critical. You have to, determine very well the boundary condition of the system. But for meteorological data, you have to, they collected all the data, precipitation, temperature data, and then also you collected the water samples and the rain samples, they measure the caloric values. For the groundwater sampling, okay, you have to, the collected wet and dry period system, you have to directly you measure the water level, and then you have to understand the hydrologic and property of system, and then use the model. For the estimation of groundwater system, we use the numerical model and chemical model. Numerical model, generally we can make a conceptual model, physical model after the mathematical model for the analytical numerical. For this study, for example, in some study, we use the Hydrus model because this is the easy model, and then it's the convenient and then common model, and then also chemical model is tracer. We especially use the chloride mass balance in this region. For example, Hydrus is the Microsoft Windows-based modeling program, which has been developed for modeling transport of water, nutrient, and the chemical element in the soil and groundwater. We have a different, the version. The Hydrus 1, Hydrus 2, Hydrus 3 dimension. We governing the equation of this Hydrus. This is Richard equation, especially in this equation, as you see that hydraulic conductivity is very critical parameters, and then in addition this is dependent on water content, related time, and then also we have to know that about the head pressure head. We know that the vertical distance of the system with the time, and then S is a sink term. And then the second one is the chloride method, chemical method. The chloride mass balance method is the alternative method that can apply both the water zone and saturate zone in long-term average annual recharge estimation. This method is based on the relation between chloride content in rainwater and then chloride content in groundwater sample can be calculated for water zone with the flowing equation. Okay, this is you see that chlorine and precipitation groundwater system. And then we did many study about this one in the region, and then you see that there's some chloride recharge of system. But we have to be careful. If you have some, you have to minimize the contamination, because if you see that any contamination problem, it's the work. Maybe this chemical recharge modeling is not working very well, because especially in the island, that like a Cyprus, that they have a sea water intrusion. This is a problem. If you want to use this kind of model, you have to be careful. The other one, for example, in this region, we have a geothermal system, hot water. We know that the hot water, cold water, and hot water interaction with each other. This is also critical. Therefore, we have to careful about this one. We did many study in the other region also, like in African regions. That Araf Rift margin. If you want to interested, you can just read this paper. Okay, groundwater recharge is essential for climate resilience and sustainable water management. Both natural and artificial recharge store water underground during wet period, making it available during dry period, serving a natural buffer against climate variability. Groundwater recharge sustain the long-term availability and quality of the groundwater and help maintain the natural balance of the hydraulic cycle. It is also play key roles protection of water quality and reduce the negative impact of the pumping, such as landslide or sinkhole. Okay, when you are planning to do ascertain groundwater recharge, you do a very good hydrological condition, because are the first and most critical consideration. You have to think all hydrologic parameters and the hydraulic parameters. In addition, you have to think about the geologic structure must be carefully evaluated. You have to think about the water availability and time are key factors. Water quality is a crucial, particularly for artificial recharge. And then also you have to think land use and surface conditions significantly affect the recharge. Environment and ecological impact must be considered. In generally, effective groundwater recharge requires, requires an integrated assessment of the hydrogeological water quality and quantity, land use, environmental impact, climate variability, technical feasibility, and also they need the governance framework. Thank you very much for your invitation, this important congress. If you have any question, I will be glad to answer.
Thank you very much, Professor Dr. Alper Baba. And thank you for everyone for joining our session. And thank you for everyone for their valuable contribution to our conference as always. Now this is the end of session 1. We will continue with session 2.